Hello, today we're going to look at nuclear fusion and the prospects of pretty much unlimited sources of energy which could replace nuclear, wind and coal power stations with much lower impact on the environment. Nuclear fusion happens when two light nuclei fuse together to become a heavier nucleus, and in the process of doing so they release energy. Now, we discussed how that happens in my video on nuclear fission and radioactivity, but basically if you look at what's called the binding energy per nucleon in a nucleus, the binding energy is the energy that keeps a proton or a neutron inside the nucleus and stops it getting away. And you look at it for each element, starting with hydrogen here, going all the way up to uranium, you get a curve which looks something like this. And the minimum point is at iron, which has 26 protons in the nucleus. And the idea is that if you look at hydrogen, which is about here, then the binding on energy per proton is quite high, whereas if you look at, say, helium, the binding energy is lower. So a proton in a hydrogen atom has a much higher binding energy than a proton in a helium atom. So if you can take, say, protons and put them into a helium nucleus, then you get energy released. That is in fact what is going on in the sun all the time. The sun is basically a big ball of hydrogen. But at the high temperatures in the sun, this becomes what's called a plasma. A plasma simply means that the electrons in the atom are essentially given so much energy that they escape from the atom, just leaving the nucleus behind. And the nucleus of a hydrogen atom is simply a proton. So in the sun, you've got lots of protons. And what is happening is that the weak interaction converts some of those protons into neutrons. So a proton becomes a neutron plus what's called a positron plus a neutrino. Neutrinos are being sent out by the sun in their billions. They hardly ever interact with anything. They pass straight through the Earth. They even go through you and you don't even notice. A positron, on the other hand, is a positively charged electron. And when it meets an electron, it annihilates and produces a little bit of energy. Well then, the proton in the sun can meet up with a neutron, which it has produced by the weak interaction, to produce what's called a deuteron. That is something that's got a proton and a neutron together. And then the proton, another proton in the sun, there are plenty of them, meets up with a deuteron, which has been produced here, to produce helium-3, which is a helium nucleus, but not quite the helium we know it. It has 2 protons and 1 neutron. Normally you would expect a helium to have 2 protons and 2 neutrons, but this is helium-3. And then 2 helium-3s, manufactured this way, can meet together and produce helium-4, which is the version we do know, 2 protons and 2 neutrons, plus 2 protons. And those 2 protons can be the protons that exist for these reactions, which are just going on. This process is going on in the sun. It has been going on for 5 billion years. It will continue for another 5 billion. That's basically all that's going on in the sun. But in the process of doing all that, it is releasing huge amounts of energy. And it's releasing huge amounts of energy because essentially protons which have this amount of binding energy are being converted into helium with less binding energy, and the difference between the two is being emitted as the light and the heat and all the other energy forms that we see. There's a problem if we want to do that on Earth. and that is that you need a huge amount of energy to force two protons together. The reason, of course, is that protons are positively charged, and if you bring them together, they will repel and try and move away from each other. So if you bring this proton towards this proton, it will divert because there will be a force pushing it apart. And in order to get them together such that the strong nuclear force can bind them, you need a huge amount of energy. In fact, you need about 1 MeV, 1 mega electron volt of energy per nucleon. So per proton, per neutron. We can relate energy to temperature. Temperature is really just a measure of energy. It's a kind of measure of the average energy of each atom or molecule. And the equation which relates them is to say that 1 electron volt is equal to, on average, 10 to the 4 degrees Kelvin. That's 10,000 degrees Kelvin. And that is related by what's called the Boltzmann constant. Well, that means that 1 MeV, which is what you need if you're going to force these two protons together, is the equivalent of 10 to the 10 K, which is 10 billion degrees Kelvin. And that's quite hot. Now, of course, it doesn't mean that when you get a temperature of 10 billion degrees, every single nucleon will have an energy of 1 MeV. There will be a distribution, as one might expect. So the number of nucleons with various energies, if we plot energy this way, then there will be a distribution. And the average will be 1 MeV if the temperature is 10 billion degrees Kelvin. At that sort of temperature, rather like the sun, the hydrogen would no longer be a gas, it would become a plasma. But it is made up of protons, since the electrons have been stripped off, and those protons are positively charged. And so you have a charged plasma. Clearly, at a temperature of 10 billion degrees, there's nothing you can put it in, because anything you put it in will instantly melt. But because it's charged, it means that you can suspend it in space by the clever use of magnetic fields.